Hi, I am Dr. Kavitha. Today we are going to see Legendre's equation in my lecture 9. It is an important differential equation in applied mathematics, particularly in boundary value problems for spheres. Here, this is the Legendre equation. Let us take that one as equation 1. Here, n is a real number, but in most applications only integral values of n are required. To find the n value, we follow the following procedure. I am giving you the step-by-step procedure now. In step 1, let us take the Legendre's equation as equation 1. In step 2, assume the solution y equal to a naught x power m, a1 x power m plus 1, etc. Here a naught not equal to 0. In step 3, we find dy by dx and d square by dx square for this solution we assumed in step 2. Okay. So in step 4, we just substituting these three things, y dy by dx and d square by dx square in our Legendre's equation. We let it as equation 1. Okay. So now the equation 1 takes this form. This is that equation after substituting y dy by dx, d square y by dx square. In step 5, to find a2, a3, a4 in terms of a0 and a1, equating the coefficient of x to 0. So first we can equate the lowest power of x equal to 0. That gives you a0 m into m minus 1 equal to 0. It makes here a0 not equal to 0 we know. So that this m into m minus 1 makes a quadratic equation. From that quadratic equation we find the solutions m equal to 0 and 1. Using that 0 and 1, we need to find the solutions now. So first we let m equal to 0. Here on equation, the further coefficients, the successive coefficients of x power m, only we equate the lowest coefficient of x equal to 0. Now equating the coefficient of x power m minus 1, x power m plus r, we get the equation 2 and 3. From that 2 and 3, we substitute the value m equal to 0. That will gives you a1 equal to 0, but actually a1 not equal to 0. The equation 3 gives a2, a3, a4, a5 values in terms of a0 and a1. Hence m equal to 0 gives you two independent solutions. That means in terms of a0 one independent solution, in terms of a1 another independent solution. Let us take these two independent solutions as equation 4 and equation 5. Equation 4 is in terms of a0, equation 5 is in terms of a1. So next we can consider the value of m as 1 and substituting this m equal to 1 in equation 2 and 3, 2 gives you a1 equal to 0 again, and 3 gives a3, a5, a7 values as 0 and a2, a4, a6 values in terms of a0. Here a0 only present, so let us take the previous solutions only, that for equation 4 and 5 only we consider the equation 4 since it is in terms of a0. Okay, so here also in terms of a0 only the solution should be. On substituting this a2, a4, a6 values in equation 5, we find another solution. So let us take that solution as equation 5. Hence y equal to y1 plus y2 is the general solution of equation 1, that means the Legendre's equation. So next, if n is a positive even integer, the series 4 becomes terminates at x power n and y becomes a polynomial. So similarly, when n is an odd integer, the 5 becomes a polynomial of degree n. Thus, whenever n is a positive integer, the general solution of 1 consists of a polynomial solution and an infinite series solution. Legendary polynomial. If the general solution of Legendre's equation consists of a polynomial and its polynomial solution with a0 or a1, so choose that the value of the polynomial is 1 for x equal to 1, are called Legendre's polynomial of order n and are denoted by Pn of x. Next, this is legendary polynomial of order n that called as Pn of x. Next one, infinite solution with a0 or a1 is called legendary function of the second kind and is denoted by Qn of x. So the legendary function of second kind called as Qn of x. Legendary polynomial of order n is called as Pn of x. Okay. So next we are going to see the RODRIGUE'S formula. We shall prove here Pn of x equal to 1 by n factorial 2 power n d power n by dx power n x square minus 1 the power n. Let us take this equation as equation 1. Let v equal to x square minus 1 the power n means we can find the next derivative of v as v1 dv by dx as this equation after derivation of one single derivation of v1. So now on substituting this v and v1 in equation 1, we find another equation that is called as equation 2. Now differentiating equation 2 n plus 1 times by Leibniz's theorem, we find this equation. On rewriting this vn plus 2 as d square vn by dx square and vn plus 1 as dvn by dx, we can find this equation. This equation is called as Legendre's equation. Here and Cvn is its solution. Also its finite series solution is Pn of x. So Pn of x equal to Cvn. We can take it. Here Vn means d power n by dx power n x square minus 1 the power n. Let us take that one as equation 3. Now determine the constant c by putting x is equal to 1 in equation 3. We find the c value as 1 by n factorial into 2 power n. Substituting this value of c in equation 3, we get equation 1. That is called as RODRIGUE'S formula. Here in this picture shows you the Legendre's polynomial. Here P0, P1, P2, P3, P4 everything you plot in the graph means you can get it. Here look at this. The only limit is minus 1 to plus 1. So the Legendry polynomial can have the limit only up to minus 1 to plus 1. That we can observe from this picture. Our observation Pn of x equal to 0 real and lie between only minus 1 to plus 1. Next, legendary polynomial, we know this equation RODRIGUE'S formula, that is equation 1. From this equation 1, on substituting n equal to 0, 1, 2, 3, we find the value of P0, P1, P2, P3, P4, etc. In generally we call it as Pn of x equal to sigma r equal to 0 to n minus 1 to the power n. Let us take this equation as equation 2, where capital N equal to 1 by 2 n or minus n minus 1 by 2 according as n is even or odd. Derive 2 from equation 1, equation 2 from equation 1 by binomial theorem. We find this term. On simplifying this term by equation 1, we get this equation. This is same as 2, the last term, such that the power of x for this term is either 0 or